I now call to order the Society's 2483rd meeting in what is now the 152nd year since its founding on March 13, 1871. Good evening, everyone.
Good evening, Larry.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium at the Cosmos Club, and everyone on YouTube tuning into the live stream of tonight's PSW meeting. Tonight's lecture will be by Prineha Narang on non-equilibrium quantum systems. But before we get to that, we want to thank our sponsors, and we're grateful to PSW full-year sponsors, PSW member Mike Helton and Helton Associates, and he is in the audience, so let's have a round of applause for Mike. Thank you, Mike. And the Policy Studies Organization in cooperation with the American Public University, and let's thank them as well. We are also grateful to PSW member Tim Thomas for his generous support of the fall lecture series, and to the sponsor of tonight's lecture, PSW member John Downing, who is unable to be with us tonight. Thank you to all of our sponsors and supporters. I'm pleased to announce the following new members. David Lopez, project manager with BAE Systems, interested in theoretical physics, astronomy, cognitive sciences, and archaeology, who learned a PSW from a PSW member. And Ting Lee, an architecture student at the Rochester Institute of Technology in bleak Rochester, New York. Wonderful Rochester, New York, who is also a classical musician and is interested in space architecture, and who learned a PSW from watching some of our videos on the PSW Science YouTube channel. And tonight's speaker, Prineha Narang, who learned a PSW from the invitation to speak here tonight, and whose interest will be clear in a small part from tonight's lecture. We welcome them all to membership. Mark Clampin will now present the minutes of the 2482nd meeting in the lecture by Lori Locascio on the National Institute of Science, Standards and Technology, prepared by Recording Secretary Camille Lance and edited by me. Mark, the stage is yours.
Good evening. President Milstein called the meeting to order at 8:05 p.m. He welcomed everyone, thanked sponsors, and announced new members. Janice Soreth read the minutes of the previous meeting and the lecture by Yuichi Suda on the Hayabusa 2 mission. President Milstein then introduced the speaker, Lori Locascio, the 17th Director of the National Institute of Standards and Technology. Locascio said she was honored to speak and that she had greatly enjoyed the discussions about fluid mechanics and artificial intelligence at the pre-lecture reception and dinner. She then turned to the topic of her lecture, the National Institute of Standards and Technology. She began by noting that NIST does measurement science and that quantitative measurement capacity is essential to all research and development activities, to manufacturing and to competing in the global marketplace. She noted that NIST has an annual budget of over $1.6 billion and a workforce of more than 7,000 federal and other workers at its main facilities in Maryland and Colorado, and at a number of joint institutes. She also noted that NIST works closely with academia and industry. NIST is structured along 3 programmatic lines. Laboratory programs that establish standards and provide calibration services to enable competitiveness, innovation and standards needs of the US industry, primarily through extramural means, and the Chips for America program to develop an integrated ecosystem for US leadership in integrated circuit technology. Locascio then said that NIST has 3 scientific and technical priorities for maintaining US industrial leadership and maintaining the ability of the US to compete in the global marketplace. Critical and emerging technologies leadership, particularly in emerging fields, standards leadership, and manufacturing leadership. She explained that the CHIPS Act is designed to ensure US global leadership and that China is a particular concern. She displayed a graph showing the growth of China's R&D spending, noted that it is now second only to that of the US, and that it is on a curve to surpass it. China and other competitors play by different rules, she said, noting that China has a national industrial policy that targets specific strategic industries and supports them with large-scale and well-funded centralized government programs, quite different from the current US approach to industrial competitiveness. The CHIPS Act, she explained, is one strategy of the current administration to maintain US leadership and competitiveness in the face of such competition from China and other countries. It is an estimated $52 billion bet on US science and technology along the lines of the Manhattan Project, the Apollo Project, and the Human Genome Project. $39 billion is to drive expansion of US semiconductor manufacturing capacity, attract large-scale investments in advanced technologies, and advance US technical leadership in related critical technologies, she said. And $11 billion is for R&D, particularly a National Semiconductor Technology Center, a National Advanced Packaging Manufacturing Program, Manufacturing USA Institutes, and Research and Development at NIST. Grand national technology and industrial programs like this are not common in the US, she said, but the few that have been instituted have been instrumental in advancing critical technologies, and she expects that CHIPS will also be transformative and create a robust ecosystem that will ensure US technological and industrial leadership. With that, Locascio closed her lecture and invited questions from the audience. One member asked how NIST decides what to fund and how markets figure into the decisions. The speaker answered that NIST not only responds to markets but also creates them, pointing out that NIST has programs specifically aimed to ensure fields are funded at the earliest stages of development. Another member asked how NIST controls the intellectual property to ensure that it primarily benefits the US. The speaker explained that NIST is required to patent inventions and license technologies, and that it has a very strong technology transfer program. And she noted in passing that she herself has 12 patents through NIST. After the question and answer period, President Milstein thanked the speaker, announced upcoming lectures, and thanked volunteers. He asked everyone interested in helping out to contact him, and at 9:51 p.m. he adjourned the meeting. Temperature in Washington, D.C., 19 degrees C. Weather clear. Live audience of 51, 30 in the Powell Auditorium, and 21 on live stream. Views of the recording on the PSW Science YouTube channel in the first 2 weeks, 221. Respectfully submitted, Mark Clampin, on behalf of Larry Milstein and the recording secretary, Cameo Lance.
We now turn to tonight's lecture by Prineha Narang, titled Driven Out of Equilibrium, Shining a New Light on Quantum Matter. Pri is professor in physical sciences and in electrical and computer engineering at the University of California, Los Angeles, fondly known as UCLA, where she holds the Howard Reese Chair. She also currently holds an appointment from the U.S. State Department as U.S. Science Envoy. Pri works on theoretical and computational quantum materials, non-equilibrium dynamics, and transport in quantum matters. Quantum matter. Among many honors and awards for her work, she is the recipient of a Guggenheim Fellowship, the APS Maria Goppert-Meyer Award, and the Mildred Dresselhaus Prize, the Max Planck Award of the Max Planck Society, the Moore Inventor Fellow Award of the Gordon Berry Moore Foundation, and the Top Innovator Award of MIT Tech Review. Pri also serves as associate editor at ACS Nano and associate editor at Applied Physics Letters. She earned an MS and a PhD in applied physics at that wonderful institution on the West Coast, Caltech. All questions will be fielded after the lecture during the Q&A session. Pri, the stage is yours.
So, thank you so much for being here. I recognize it's late in the day, so I really, really appreciate that you're here. And those of you who joined for dinner, thank you. The conversation was very stimulating, and I'm excited to tell you about some of the work that we started talking about at dinner. And I was trying to perhaps use my hands to describe equations, but there will be equations here. Okay, so I'll tell you about work we've been doing in driving quantum matter out of equilibrium. And something I want to convince you of tonight is that being out of equilibrium is absolutely awesome. Okay. So like many of you, I've been thinking about what are we doing? What's our overriding challenge that we're trying to address? And this was a particularly acute question in my mind during the years of COVID and returning to the office after that. And I was drawn to this story. This is a story from Sheldon Glashow that talks about our challenge as scientists, but through the lens of an alien that visits the Earth. Okay, so stay with me. There aren't any more aliens in this story beyond this little component. But this alien lands. Of course, they land in New York City, because why won't they? And they show up. They're at Washington Square. And what they observe is a couple of people playing a game of chess. Now, of course, this is middle of the day. These folks have nothing better to do than playing a game of chess. But what's important is that this alien observing these people play this complicated game, this is the first time this alien has seen this, recognizes that there are two challenges here. One, to learn the rules of the game, and the second, to actually become a grandmaster. Essentially, to go from an observer of the rules, to understand the rules, but to actually be able to be a choreographer. And I think what we're doing in quantum matter today, the work that we're doing in non-equilibrium control, in particular of quantum matter, resembles more choreography and less of that observation and understanding of the rules. But we couldn't have gotten there without some understanding of the rules, some understanding of how we can actually control these non-equilibrium interactions. So why non-equilibrium and why now? Well, some of you have probably been thinking, what are all these interactions we're going to talk about? What is non-equilibrium, and where does what we observe as humans sit? So human perception sits somewhere on the right of this slide. Turns out that we're not very good at observing things that are out of equilibrium. From our perspective, most things, even though life, galaxies, quantum matter are not at equilibrium, it kind of looks like it is roughly at equilibrium. But that is not actually where we would be if we could measure things at faster and faster timescales. So it turns out there is, over the last several decades, a lot of work that's been done in developing new sources, new detectors, and new kinds of technologies that allow you to think about a very large set of timescales. That was not intended. So going all the way from, say, a few milliseconds down to the attosecond timescale. And I'm going to talk about attosecond here in a second, a very, very timely topic. So when we think about the types of physics that lives, say, at nanosecond or even picosecond timescales, it's still very exciting, and it still is out of equilibrium, particularly things like spin excitations, thinking about energy transfer, whether it's within the same molecule, whether it's between a couple of molecules, types of emission processes. But then as we get faster and faster on this timescale here, you start to realize that actually things get very, very hard to describe as being small perturbations away from equilibrium. So this is a secret that a lot of theorists employ. We say most things live at equilibrium. In fact, better yet, let's put it at zero temperature, right? Even better if it looks like it's a 1 or maybe a 2 particle interaction. Life would be good. Turns out that non-equilibrium dynamics, particularly all the action happening on this end of the spectrum, starts to question some of those assumptions, particularly assumptions about being slightly away from equilibrium as being a good descriptor. So, for example, calculating something about the ground state is not always sufficient for us to describe some of these phenomena. I digress. So why are we talking about these phenomena this year, and why am I talking about it particularly at this lecture here tonight? Well, the Nobel Prize in Physics this year was awarded for work in attosecond physics to Piero Agostini, Ferdinand Krauss, and Annie Earlier. I definitely mispronounced all three of those names, but hopefully they'll forgive me for that. And what I want to point out is that this prize actually recognizes some of the work that has enabled the field to access this time range, to access some of the physics that was really hidden to us, some of the electron-electron dynamics, some of the phenomena that we would not have had access to without the sources that developed. And here, source is really an optical source, though, of course, we could also talk about X-ray and other types of free electron sources that are of interest. So, now, you might think, what is an attosecond? How do I experience an attosecond? And this graphic from the Swedish Academy of Sciences actually was particularly helpful. So if you think of the human heartbeat, it lives in the middle of this spectrum. On one end of it is the age of the universe, which I'd say is very, 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 very long. And on the other end of it is an attosecond. And turns out these are not quite equidistant, but the heartbeat sits roughly in the middle there. So just to kind of give you an idea of something that is very, very fast, something that is, of course, extraordinarily long, and yet the fact that we want to try and understand things across this time range. Okay. So there have been a lot of advances in ultrafast techniques over the last few years. And I want to emphasize that some of these techniques have really allowed us to think about quantum matter where the quantum interactions are more important than, say, other types of interactions. So some of these techniques have given us access to interactions we knew about, we could predict, but maybe not observe in real time, and certainly not control with the same level of control that we can today. So for example, we now have the sensitivity to changes in topology. We can actually very clearly switch topology. We can change various types of symmetries, and this is by using the drive, that excitation, right? So now we're going from thinking about the drive, that excitation as just being a way to observe, to actually choreograph, to actually control the interaction that we're interested in. So we can figure out what are the types of interactions we're interested in. This could be, for example, collective excitations in our types of quantum matter. It turns out quantum matter has beautiful set of excitations. It could be related to the spin physics. So we could think about the magnons. We could think about all different kinds of ways that the photon excites, say, phonon polaritons, excites all kinds of interactions. By the way, the word polariton here is a fancy way of saying it interacts with light. And when it interacts with light, it takes on this hybrid light plus matter form. Okay? So in some of these techniques, the focus has been, of course, more recently to control quantum matter, not just observe the changes that are happening. And that's where some of the work that I'm going to talk about tonight enters. Right? So you'll see mentions of a wide spectral range. I'll talk about some of the work we've done all the way out at terahertz and frequencies that involve nonlinear terahertz spectroscopy even, down to the microwave, and perhaps if I can squeeze it in, some of the recent work we're doing at X-ray free electron laser sources. So in all of these scenarios, there are questions. How do you excite? What are you coupling to? Is that all we couple to, right? So I come in with a photon, and if you want to see what a theorist's view of such an interaction looks like, it's as follows. I have light from this wide spectrum. I pick what I want. It is shining on my sample, and I can get it exactly where I want, perhaps at the right spot size, so I'm only exciting the part of my material that I'm interested in. Okay, no problem. That's not too hard to do. But from there, you go and think about, okay, how am I going to measure it? Am I thinking about, say, exciting a particular quasi-particle? Is it going to excite other things within the material. A good example of that is just exciting the electrons is hard. Turns out over time, you also excite the lattice, things start to thermalize, other processes take over. You could think about types of polaritons that I alluded to. Well, it turns out when you excite one type of polariton, sometimes they can couple to other things. So when we were talking about predicting some of these light-induced states of matter, there are a lot of questions that emerge about exactly what you're coupling to and how quickly are things thermalizing, okay? So we're talking about non-equilibrium, essentially about things that are non-thermal, but eventually, at some point, things will thermalize. And we want to make all of our exciting action happen prior to that thermalization. So as we do that, and this is usually about the point, I know folks are not going to do that here today, but there'll be a question. How is this different from all this stuff we've seen so far, where you shine a giant laser on something and something happens, right? So I want to convince you that this is fundamentally different because we are observing states, whether it's in materials, whether it's in molecules, whether it's in very strongly correlated or slightly correlated types of quantum matter, that is fundamentally non-equilibrium, stuff that is not thermal. There are various ways I could say this. Another way I could say this is that temperature is not a good way of describing the system at that point. It's not a well-defined quantity for these systems, or just the fact that we're not just heating up our material, we're not just heating up our system. What we're actually doing is exciting very precisely types of interactions, okay? So if we were just probing, right, and just probing would look like something on the left, this would be that simple picture of observation. And I keep calling it simple, and it is sometimes simple, not always. And I could talk about it as, say, being some electronic or lattice coordinate relative to some potential energy surface. What is a potential energy surface? It's just the energy landscape of our excitation. And it turns out that most things, when we are probing them, live at the bottom of this trough. And when you excite them, they wobble around there. This is what you would essentially think of as a slight deviation from perturbation if you got maybe out here, maybe you got to some part that looked slightly nonlinear. What we're thinking about now, of course, are phenomena where you're switching. Perhaps you're switching between two degenerate ground states. These are ones that have the same energy, but you could switch between them for various reasons. Talking about something that perhaps is a slightly higher energy, but not high enough to call it a strictly an inaccessible state. Talk about critical phenomena, or even nonlinearities. The one that's been very, very popular recently is, of course, nonlinear phononics. This is where you're accessing several different phonon degrees of freedom via the excitation. Okay, so all of this to say, why are we doing it? This is a lot of work, right? There's a lot of excitation happening. There's a lot of energy going into the system. And I'll just maybe try and preempt that question with a provocative result, and this is one from several experimental groups now, where they talk about how even a cuprate, in this case a parent cuprate, can actually, and this is something that's been studied now for decades, folks in the high TC world have thought about it quite precisely for some time, but the claim that certain experimental groups have is that by driving the system, particularly by driving and modifying the pairing glue, the glue essentially believed to be responsible for the superconductivity in the system, you could actually think about stabilizing it above its transition temperature. This is a provocative claim because the idea here is that somebody's driving a system and stabilizing it. That should be counterintuitive. That is the opposite of what every low temperature physicist has been trying to do forever, which is to take energy out of the system, cool it down, very, very precisely think about it, as opposed to actually pumping energy into the system, which tends to have the impact of actually the opposite of stabilizing the condensate. So just one of the many, many claims that exist in this domain. And if you look at the timescales here, by the way, they're very forgiving. These are picosecond timescales, many orders of magnitude slower, than the fast attosecond behavior I was just talking about. So there has been a set of claims, say, around transient superconductivity and related ideas. Okay, so all of that to say that this is in fact different. there is, in fact, a lot of work in creating new kinds of non-equilibrium states that we couldn't do till very, very recently. And now you might say, from a theory standpoint, why is now the time, right? Everything so far maybe has convinced you that experimentally now is the right time, but why now from a theory standpoint? Why is the theorist thinking about this problem? Well, we're thinking about it because correlated electronic structure methods, the types of techniques you would use in order to describe such phenomena, the ways that you would describe either the ground or the excited state manifolds associated with these types of interactions, actually was incredibly hard for a very long time. And it remains hard. I don't want to trivialize the work that's happening in the field, but we've gotten to a point where we're able to synthesize methods from a variety of different fields, a variety of different techniques that rely on large-scale supercomputers to actually describe these phenomena with, say, some high fidelity without making too many assumptions. So on the right of this slide are methods that our physics colleagues in the audience, particularly if you're a condensed matter physicist, will recognize as being quite common. You think about the phase diagram, perhaps you think about your crystal, and the operating assumption there is that there's some well-defined periodicity that you can invoke, so you downfold the problem to some a component of it, right? And you say, okay, well, the rest of it is just a copy of it. It's going to be a lattice that's, so, okay. Well-defined notion of periodicity works sometimes. Turns out very, very accurate methods in the field have been developed on the left side of this slide. And hopefully folks who are online can see this pointing that I'm doing with this laser pointer. Okay. So things on the left of this slide come from a community of folks working in quantum chemistry who think about finite systems, okay? And finite systems here are ones where you're treating 3, 4, maybe a handful of atoms, or in case of some of these techniques, actually a handful of electrons, but you can treat the full many-body problem directly rather than simplifying it by invoking this notion of periodicity. And the name of the game now has been to actually merge methods from the left and the right of this slide, come to somewhere in the middle where we can actually describe the types of non-equilibrium dynamics that are really of interest. And also, in all of these scenarios, like I said, we're interested in the ground state. Knowing something about the ground state is very, very useful for us. It gives us an idea of what kinds of collective excitations would be allowed to begin with, but also understanding the excited state manifolds, the types of things that live above that ground state is incredibly important to us. And I see some of you in the audience who are engineers, so I'll just say this is all very useful too. There are advantages of doing things away from equilibrium. And you're probably maybe tired by this point of hearing that quantum computing is going to change the world, so I won't reference that too much. But I want to say that there are all kinds of different quantum systems, and they also do not live at equilibrium. And understanding things away from equilibrium actually could realize some of these technologies, and perhaps some of the types of building blocks we could get, perhaps the kinds of building blocks that use some of these non-equilibrium components could actually be directly used in devices that realize or scale these quantum systems. At the very least, I'll say that if we think about large-scale quantum systems, photons will be involved somehow. And when photons are involved, things are away from their ground state, things get excited, photons have a tendency of doing that. So there is a reason to think about optical excitation of quantum matter, even if it doesn't directly give us a quantum computer tomorrow. Okay, so that was my little spiel for how this will be useful. Now I'm going to return back to how we think about these interactions and how we could go about describing them. Okay. So when we think about light-matter interactions, and this is now a theorist's view of the world. There is light on one axis, there's matter on another. We're going from very analytical techniques to computationally intensive techniques. And the techniques you might recognize, or the names you would certainly have heard of on the bottom left of this chart, are ones where we would say think about a lattice model, we would think about a Jaynes-Cummings type Hamiltonian, perhaps we'd invoke ideas that come from quantum optics, right? And why would we do that? Well, quantum optics provides us a very complete description of how things behave, particularly when you have a few photons, you have some involvement of the vacuum state, and it's modifying the behavior of matter somehow. So would that be sufficient to describe some of the problems? Yes, some, but not all. Turns out that on the other end of this slide are approaches from electronic structure theory. And pick your favorite acronym. It could be coupled cluster singles doubles. This is a gold standard. My quantum chemistry colleagues love talking about it. And for that CCSD T, you can add even more letters that then talk about the level of accuracy you're headed to. The problem with most of the techniques in the context of the problem we are trying to solve here is that they include the photon almost always classically, which is to say that if you were thinking about how the vacuum state is involved, you're thinking about the quantum nature of light entering the problem, these methods would disregard that. On the top left of the slide, you'll see approaches our photonics colleagues have used very successfully for quite some time. These could be transfer matrix methods. These could be ideas involving photonic crystals. All of these descriptions, and pick your favorite FDTD or finite element software, these methods rely on some epsilon or chi, some way of describing the optical response of the system as a function of the frequency, as a function of omega, and something I can calculate for the system and then input into these models, right? But that isn't necessarily allowing us to think about how the photon is then going to modify in some way the behavior of the matter itself. Okay. So we and others have been now thinking about a generation of methods, and this is really actually tracked a generation of students and postdocs that have come through some of our groups, where we merge quantum electrodynamics, something that keeps all the best things that we want about the photon, together with electronic structure methods, both formally and computationally. Okay? I want to point out that there were certain challenges in doing this formally. Those have been overcome. And now we're primarily dealing with the challenges of doing this computationally. Okay? So lots and lots of acronyms, lots of methods. But really, what am I talking about? Right? So within electronic structure, there are a whole bunch of approximations, and we tend to think of them as this ladder that eventually will take us to some proverbial electronic structure heaven. But as you get rid of some of those assumptions, you become better and better. But of course, you increase the computational cost very, very rapidly. And here, computational cost refers to calculations running on a classical but very, very large supercomputer. The types of systems we use are similar to a large GPU system. We think about using, and not just think about, use the Summit supercomputer, now use the Frontier supercomputer. So these are really the state of the art in how large a system you could actually simulate. But even with that, if I formally combine quantum electrodynamics and one of these very hard to pronounce electronic structure methods, which we have, like coupled cluster singles doubles, my ability to do a real problem very quickly diminishes. I can do a great job if I have QED plus some way of describing this problem using, say, a mean field approach. Mean field approach is exactly that. I look at an audience and I say, oh yeah, people are roughly in this configuration. That configuration roughly represents the state of the system, the state of the room, right? And that's a mean field description. I can do that. I can do QED plus mean fields, and I can do that for a large system. But the instant I try to actually retain some of the computational detail, life gets very hard. So what we've done is found a way to incorporate QED plus time-dependent density function theory, QED plus coupled cluster, and found a way to do this for real enough systems. Okay? So our first foray into this was to actually, and this is one of my few slides with equations, don't worry, I took out anything that invoked Tyson equations, I took out anything that had diagrams, I did some TLC before the talk. Okay, but this I have to do. Okay, so our full physical system is quite complex. Right? I told you we have interacting electrons, we have nuclei. By the way, there's two reasons to include nuclei. There is no talking about phonons without having the nuclei there explicitly, and there's no talking about temperature in a physical manner, or thermalization, to be more precise, without having the nuclei there somehow. at least not in the types of systems we're interested in. And of course, we want the photons, right? And without light, no go. So we map it onto an effective cone-sham system. And the trick here, you would say, well, this is too good to be true, right? I go from this large interacting problem to now thinking about this being it's non-interacting, non-interacting, non-interacting. What gives? What gives is I need to find a good mean fields exchange correlation kernel, right? And I can have a one-to-one map. I can show that a one-to-one map or one-to-one correspondence would exist. All I have to do, right, weekend's worth of work, is find that exchange correlation kernel, find that map. As soon as I have that map, no problem. So for certain problems, we've been able to find this map, and we've been able to show that you can do this problem, and you can do this explicitly to think about both large molecular systems and also low-dimensional materials. And to me, low-dimensional materials mean, say, a single layer of graphene, a single layer of a graphene-like material, things that are quite simplified. Not quite at the point of talking about that very complicated YBCO crystal, that parent cuprate compound that I showed you, with all of these degrees of freedom incorporated, right? So as we were working on this, that question came up, and I know it won't come up here because we are not going to ask questions as we go along, but I prepare for a condensed matter theory audience, which by now would have raised hands several times and said, really, but how is this going to work for something that we're that's complicated, that we're really interested in? So towards that, one of the students who worked with me, now a junior fellow at Harvard, Nick Rivera, said, well, how about we have this idea of photonic quasiparticles? And I thought, well, that sounds weird, right? Because whenever you have the photon, excite something, we just talk about all of these as quasiparticles. So what's a photonic quasiparticle? Well, the idea was to go from a system that is quite complex, say has many levels, and Cavity talk about it explicitly, to approximate it with a few level system. And now you have these handful of excitations, and handful here really does mean a handful. But now you take some of that complexity and absorb it into the properties of the effective vacuum being modified. And that allows you to get around some, but not all of the problems associated with the previous method I told you about. So in this scenario, the good thing is that, yes, you have a few levels. Perhaps you're somewhere between that quantum optics approach, but not all the way out to that electronic structure approach that I alluded to. But you can access non-perturbative ground states, and you can think about things that are in a very, very, very strongly coupled domain. So this could be ones that involve superconducting cavities. This could be ones that involve some very pristine EMO systems, but also more messy systems that we come across in condensed matter. So then, at some point, as we were working on this problem, and I really kind of continued to avoid this superconductivity thing for most of my career. I would find, I'm walking along, there's a problem I'm trying to solve, superconducting, something would happen, I would just kind of go around it, keep going. But this time, I couldn't avoid it, and this is where working with Victor Galitsky comes into the picture, where it was suggested, well, how about, instead of worrying about controlling the entire superconducting condensate, which is work that a postdoc in my group had done as a graduate student working in Victor's group, he said, well, let's solve a simpler problem. I promise it's simpler. And the idea was that you could perhaps think about modifying the magnons, or think about the magnon polaritons that can be excited in these cuprate superconductors, and use that perhaps to indirectly control the condensate. And this, at its outset, seemed quite simple, because this could be done using terahertz cavities or even metamaterials. And I talked to some of you at dinner who talked about working in photonics, and in particular in metamaterials. And in this context, there was a particularly elegant idea that we could have a metamaterial tape, right? And it would have these nice resonators. Somebody would pattern them. Somebody would then lay out this tape on top of superconducting material, and voila, we would have control over the superconducting condensate. So things are never quite that easy, by the way, that graduate student who then became a postdoc in my group is pictured here, John Curtis. And the other graduate student who worked on this, Nick Poniatowski, was an undergraduate at the University of Maryland. So I see there are a lot of folks in the audience from the University of Maryland. So yay! I'm glad that so these students have come and worked with us. Okay. So in this context, and the idea was perhaps instead of directly coupling to the magnon, first we could do something slightly clever, couple first to the phonon. This would now give us a phonon polariton. Remember I said polaritons come in many flavors. It's like going to the bar and ordering your favorite cocktail. You could pick, there'd roughly be some ingredients that are common across these cocktails, but then the way you go about it could be quite different. So our approach was first couple to the phonon, excite a phonon polariton, and then couple to the magnon. And we wanted to contrast that with this direct approach with the cavity controlling the magnon. And in this scenario, we were able to find mixed success. One of the things we saw is that, yes, this approach does work, which lends some ideas in this lattice-mediated control, which I'm going to talk about here in a second. So this idea of controlling via the phonon, via the lattice, is a good one. Though what we concluded is that perhaps this would be a little ambitious to do with this type of cavity directly. Now, are there more clever types of cavity designs? Absolutely. Could we think about doing this in different spectral bands? Yes. This was just our initial idea of how we could go about it. Okay, but that stuck with us because IR active phonon, right, or any optically active phonon is something that we like being able to access from those nice ultrafast methods, right? And the thinking was, if all I need is just the right phonon to modify the other properties of this material, I'm in good shape because I know that there are various phonons I could access. Here, there's a very obvious C-axis phonon, but even if it's not that obvious, I know we can access it, and we can actually do some control. So one of my colleagues calls this the right shaky, right? Because all I have to do is shake the lattice just the right way, and I have lattice-mediated control, right? Saying lattice-mediated control sounds very serious, so let's just call it the right shaky. And the right shaky in our context, turns out, is very rich and gives us many options. And now, instead of talking about directly controlling the superconductor, which is a very complicated problem, one that many will debate, let's come back to my preferred approach of picking a simpler problem. Let's just control the magnetic properties, right? And this also, by the way, is useful. Turns out that if you want to make faster memories, we want to think about how we could make more efficient memories. You really don't want to run out of hard drive space on your phone. If you take a lot of videos like I do, this is a problem that becomes pretty acute, and forget to cloud backup, okay? So okay. There are ideas that perhaps we could control these magnetic properties directly by excitation. And in this case, the idea was that if I start out with, say something that's an antiferromagnetic ground state, by exciting it either with linearly or thinking about circularly polarized or in other ways polarized light, in this case rotated 90 degrees, I could actually create different driven states, and I could show this as switching behavior, right? So this idea, and there's a whole field of people thinking about this in ultrafast spintronics, has really caught on over the last few years, and I think is a simple but hopefully elegant demonstration of this right shaky. Because in this case, turns out you can drive the magnon directly, you could drive those spins directly, but you don't have to. You could pick just the right phonons. Okay. And lattice-mediated control, vibrational control, right shaky, these are all non-equilibrium phenomena, okay? And around this, there have been a series of claims. There's been a series of papers, and those of you who still get the archive mailer, I still do, will find that there are papers every day that talk about how you could actually do non-equilibrium control of some of these excitations. So you can think about, you can continue to think about phonon-driven superconductivity. You can think about phonon-driven ferroelectricity, switching topology, and also for directly addressing some of these magnetic excitations. And now the set of systems you could access, the types of materials, is actually very broad, as is the spectral band where you can do this. So when you think about this, and at least when we started thinking about it, the first question was, well, how is this different, right? So this is light interacting with something that is magnetic. We know that as magneto-optic or optomagnetic effects. We've known this for some time. This is the type of society where perhaps talking about the Faraday or the Cotton-Mitten effect, or talking about the inverse Faraday or the inverse Cotton-Mitten effect. These are things that have been known literally for the last century. So how is what we're doing different? Well, in our case, everywhere you see the word opto, we're going to replace it with the word phono. Okay, I'm not intending to say the word photo and mispronouncing. I intend to say the word phono, because that's what that right shaky shaky to me means, that you excite via light, but instead of exciting the magnetic response directly, instead of thinking about directly accessing the magnons, you are now first exciting the phonons, and then via the phonons, via say a spin phonon type coupling, you're then exciting the magnons. And of course, that two-step process might sound inefficient, but turns out that actually confers the degree of control we're interested in. Right? We directly drive the system. We have some, but not all the control we want. Going via the phonons actually, counterintuitively, at least for us, confers more control. And as theorists, we like to look at these effects, and we also like to classify these effects. There's always this tendency to say, okay, let's write down the Hamiltonian, let's think about what it looks like, and let's think about what that response, if there's a first, a second, or higher order effect that we can categorize these as. So we proposed, and this was first proposed and then experimentally realized, order matters, that for magneto-optic and optomagnetic effects, the optomagnetic effects that will be most relevant for us are the inverse Faraday effect or the inverse Cotton-Mitten effect, actually do have direct phonon analogs, and they're the phonon inverse Faraday effect or the phonon inverse Cotton-Mitten effect. By the way, if any of you comes up with a cool acronym for these that I don't stumble over, please let me know, because every talk I give, I've found myself saying that a few times and then eventually stumbling. Okay. So in this case, we're coherently exciting the phonons, okay? We're not blindly exciting them, we're coherently exciting them. And that's in part what confers the control. The other thing is that it's not just any phonon, it's a well-chosen phonon. And because of that, we actually have a lot of control over these systems. So if you're used to thinking about, say, the inverse Faraday effect, this phonon inverse version of it looks very similar. In fact, the same way that you would predict an optomagnetic field associated with it, you can predict a phonomagnetic field. This is work that was led by Dominik Jurczyk when he was a postdoc in the group. He is now a junior faculty member at Tel Aviv University. So what Dominik realized is that you could describe these effects in existing systems, but it would be even better if you went to the library, found a set of tables of these rare earth trihalides, and not only found this table, and literally there was a set of tables, this is a physical text he found, and I was quite amused by that, but you could actually find materials where this effect, this phonon inverse Faraday effect, would be very, very large, so large that in fact you have the ability to use the word giant in the title of a paper, something that I have wanted to do ever since I entered the field. Okay, so why this rare earth trihalide? Why go through all the trouble? Well, the one we picked is cerium trichloride. This is one where we had enough data from these tables that we could compare some of the things like, well, has somebody made it? Does it exist? Does it exist at a temperature and pressure that is favorable, that sort of thing. But with that, we realized this is a system that has phonons of two different chiralities that we could excite, right? So now I've introduced another component to it. First, I had phonons. The phonons were coherently excited, but they were just phonons. And now I've made the claim that these phonons have handedness, and in fact, which handedness you excite allows you to actually control this effect as well, or at least that's what I'm going to build up to, right? And chirality, and thinking about chirality in quantum matter is quite exciting. A lot of people think about it now. Folks in chemistry, of course, have thought about chirality and separating out the various enantiomers for some time. This is whether you have a right or a left-handed, say molecules. Turns out how you break that symmetry. Our hands are the best example of this. I use both my hands, but then I have to drop the mic. Okay, so in this context, the question was, this material itself is achiral, right? It's very symmetric, but how am I finding chiral phonons in it? And more importantly, how am I actually driving these chiral phonons? So we're able to kind of think about that from our calculations. We were able to not only talk about what these eigendisplacements would look like. So the cerium would map out this circular orbit. From the chlorine, which sits around it, you would get these elliptical orbits. And it turns out that it also has a fairly interesting high spin structure here, which allows you to get this very, very large spin phonon coupling. I want that large spin phonon coupling because once I excite the right phonon, I want it to transfer all of that energy to the spins. I want to be able to directly control that. I don't want this phonon to start interacting with other things, because as soon as it starts doing that, this preferential control aspect kind of goes away. Right? So I do that. And in this system in particular, we're able to show that these fields are really, really, really large. Okay? So let me convince you of that here in a second. Hopefully this is showing up at a resolution that folks can see. I come in with a terahertz pulse, and that's shown here in green. And I'm exciting two different phonon modes. Remember I told you they're different chiralities. They're both E1U modes. One is at 4.8 terahertz and the other is at 5.9 terahertz. That matters because that's a spectral band where I can actually, I have good sources, I have good control. It's not a particularly challenging regime to access. And in both cases, I start to see that actually I get some response, but certainly for the 4.8 terahertz mode, I get a very large response. This plot, maybe for ultrafast spectroscopy experts in the audience, is a good one to look at. Most people like to look at this one here, which is now showing the effective magnetic fields that I excite. Okay? Now the word effective is very important here. In optomagnetic as well as phonomagnetic effects, we're talking about effective magnetic fields, not the kind that we're interested in when you say go to the fridge and have a little picture you want to pin up there using a magnet. So we're thinking about effective fields that essentially give us an exciting response, but are distinct from the types of fields that we interact with in other contexts. And here you see, this is now in Tesla. This is not in millitesla. We get a very, very large response. In fact, comparing with other results out there, we're able to make a claim that you could get an effective magnetic field of above 100 Tesla using this system. Okay? And this is an experiment that folks are now working on. Cerium trichloride is one example. Certainly not the only one, and in fact, we've now expanded this to a larger set of systems beyond the rare earth trihalides, again, towards this idea of using ultrafast spintronics. So when you start looking, and when you start looking at phonons in particular for control, turns out the parameter space is really, 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 really large. And you could think about going via the infrared active phonons. These are ones we're more commonly interacting with. You could also think about going via just directly this magnetic infrared resonant Raman effect, which is separate from these infrared active phonons exciting the Raman active phonons. This is accomplishing the same goal, but essentially thinking about in the electromagnetic field, either using the electric or the magnetic field component of it in order to get the excitation that we want. So when we first started putting these ideas out there, and if you are looking at some of the dates here, you're thinking, this is all COVID time. I wonder if this is all theory. So we got that question. We put out this paper. This is now what I would call a deep COVID paper. Nobody was really, really doing that much in the way of experiments. We would reach out to people and say, hey, I have a thing. Will you please measure it? And they're like, no, we're going to focus on doing our critical experiments in this domain. Fine. we'll put out a theory paper. So we said, instead of doing an experiment, how do we put a picture of an experiment? This is a theorist's view of what this experiment would look like. I have a pump, I have a probe. I'm looking at some magneto-optic response here, and that's what I'm interested in measuring. But as we started doing that, we realized, well, why limit yourself to one phonon, one magnon? Right? Everything that we do in photonics involves some kind of up conversion or down conversion type process. Why not do that here? We could think about nonlinear up conversion. We could think about using the magnons for down conversion. And now suddenly we have access to the entire spectral band. And some of our reviewers during that time, first we sent this to a very, very snooty journal, and they said, no, you got to have experiments first. So we said, fine, we'll be happy publishing this in a journal that we read. So as we did that, we actually started to find that there were still some experiments that could happen. And in collaboration with some of our colleagues, particularly with colleagues at the Max Planck's, we actually started to find this evidence for fundamentally non-equilibrium dynamics, but also for some of these up conversion type processes. And so my story will bring you now to a material that some of you might be familiar with. I see at least one person in the front row who is familiar with this material, but maybe you're not familiar with this material. This is essentially an ABO3 perovskite. This is a YTO. It's been around for a while. Lots of people have thought about it. It has lots of stuff happening. It has all of the spins. It has a bunch of orbitals. It's as you might expect, it has interesting ferro and antiferromagnetic behavior. In fact, it sits at the boundary of those two. So it's something that you can, via a tiny distortion, essentially go from one part to the other part of the phase diagram. Turns out this genre of distortion happens in sufficient number of systems. It's called gadolinium ferrite type distortion. And if you can't pronounce that, that's okay. It took me a while to do that. And for things that sit at this boundary, you can kind of, using the right distortion, push them across this. So a smoking gun signature in our mind would be as follows. I pick the system, I pick the right phonons, and I pick a phonon that allows me to stabilize one type of order, and I pick a different phonon that allows me to stabilize the other kind of order. And I show that by driving the system, you can pick which kind of order is preferred. And if I can do that, I've established at least several of the things that we have been talking about theoretically. So things are never quite that easy. But in this case, turns out that they're pretty close. So we picked not just 2, but 3 phonons. And there's a 4 terahertz, a 9 terahertz, and a 16 terahertz mode. They're well chosen because not only do they couple, but they also have a large magnetic field response, and that's useful. This work, by the way, appeared some time ago in Nature. I don't know why I still have that listed as in press. But while we were going through this, we realized, well, we could have picked all of these other phonon modes, but these are the ones that have the largest magnetic field response. So now I have to drive these phonons. I have to stabilize, hopefully, one preferentially over the other, so either the ferro or the antiferromagnetic state. And I have to be able to establish this via some kind of probe. My probe here will be a time-resolved magneto-optic Kerr effect measurement. These measurements were done by Ankit Disa. Ankit Disa was at the time a postdoctoral scholar at the Max Planck's. He's now a junior faculty member at Cornell. And what Ankit realized is that not only do we need all of those things, we actually need to very precisely align this crystal, because in order to claim that we are seeing a rotation in the magneto-optic response, we actually need to very precisely know how the crystal was oriented to begin with, especially if you're claiming something associated with the B2U modes here, as opposed to, say, a different axis. So with all of that, doing this over a different set of fields, temperatures, fluents. Fluents, by the way, for those of you who are tracking this and have thought about laser experiments, we're not melting anything. We're not destroying anything. We can. Some of these experiments that has accidentally happened, but we're not actively doing that. So nothing is melting, okay? You'd be amazed at how many times that question came up. So what you expect is that for a particular kind of order, you would see a certain magneto-optic rotation. This is a rotation we would track. some number of milliradians. And then for a different order, the rotation would go in the other direction, right? That would be the inherent kind of feature to track. And that is almost exactly what we see. So we see two different phonons, 9 terahertz and the 16 terahertz mode, where we have rotation that goes a particular way. And then, of course, you see that the 9 terahertz mode really shows a spectacular response. With the 4 terahertz mode, you see a rotation in the opposite direction, right? And this is because the 9 terahertz pump mode is actually stabilizing that ferromagnetic order well above the transition temperature. So if you look at the equilibrium transition temperature here, this is one, no drive and nothing, you'd say it's about 27 Kelvin. By driving the system, we're actually out to a very, very exciting 80 Kelvin. So this is saying that it's not a small correction, but now we need to understand exactly why that is. And I see that, speaking of correction in times, I will soon start to run out of time. Just want to say that there are multiple timescales involved here. And in our case in particular, we took a while to understand whether the phonons are allowed to relax back. Is there a bottleneck? You see there's a very quick rise, and then the behavior persists for a very long time. Why is that? If it responds very quickly, usually you would say it also thermalizes very quickly. But in this case, we see different behavior. We start to understand both the rise time as well as the decay here, and essentially realizing that even during ring down, so even after the drive is turned off, the system effectively feels like it is driven. It effectively remains driven for a longer period of time. So reconciling this and understanding it actually was quite critical. And everything that we've seen so far is aligned with that phonon inverse Faraday effect prediction that we had from a few years prior to this work being out. So going further, and this is still in the single phonon, single magnon picture, we started looking at yet another well-established, but still a system that is giving us new physics, erbium ferrite, EFO, where we've seen terahertz-driven magnon upconversion. And now, for those of you who have read any of the nonlinear optics textbooks, my personal favorite is Bob Boyd's textbook, you start to see all of these processes that become available. Right? And you can say, okay, well, everything I could say make happen with nonlinear optics, I can now replace with nonlinear coupled magnonics, and it gives me fundamentally new access to some of these types of quantum matter. Okay? So that was all very, very driven and very, very condensed matter focused. But in my abstract, I promised you that we would not limit ourselves to condensed matter. We would actually make the jump from condensed matter to actually some of the high energy physics proposals that have shown up in this field. Of course, there will be a non-equilibrium component to it. And this is not new in the sense that in condensed matter, we've been borrowing ideas from systems, types of particles predicted in high energy for quite some time. But something I'll show you over the next few minutes is that this need not be a one-way street. There are systems that we can realize, types of quasi-particles we can find that are analogs to our high energy physics proposals that actually do teach us something about the high energy theory. And hopefully we'll also have enough time to talk about axions. So I'm looking at the time and well, yeah, can't see that far. So there we go. Okay, so the story starts with knowing something about how, say, these particles are described and how you would perhaps invoke something that is a different way of thinking about this potential energy landscape. So remember I told you we're just looking at some energy landscape and taking a slice through it, and that was one of the very first slides I had. But that is truly a slice. In most cases, we ought to be looking at something that looks like this this inverted hat, this inverted bowl, whatever picture whatever thing this picture does for you. A sombrero type potential goes by many names, where you have the Goldstone mode, which is one that goes like this along the brim, and then the Higgs mode that goes like this along the brim. So imagine me wearing a giant hat, and I'm talking about the brim of the hat, right? So this actually is something that you can easily access, this kind of dynamics. You can do that perhaps if you think about exciting a structural order parameter. So when you have a potential like this, particularly one where you can take some many-body behavior, map it to it. Most people in condensed matter would refer to it as the order parameter, and then you'd be talking about the dynamics of that order parameter. But it's a fancy way of saying, what do these excitations look like if I could excite them in some part of the spectral band? And in this case, now we're looking at a hexagonal manganite, which has a structural order parameter that maps out this Higgs mode and Goldstone-like mode. And in our particular scenario, the Higgs mode is optically accessible, but the Goldstone mode is optically silent. Something we show is that you can excite the Higgs mode, decay into a pair of Goldstone modes, and actually this represents a very nice coherent transfer of energy. This is something we started to do in part because we wanted to show that via this decay you could even start to create entangled pairs using this symmetry. But as we went further along that road, right, and so if you remember that brim, right, so I'm talking about going like this or going like this, those are essentially scalar potentials, thinking about it in a very kind of scalar response. We immediately realized that there's types of quantum matter where you could find things that have an axial or vectorial component that you can incorporate. And for those of you coming from high energy, this should be very scary because now I'm claiming that there is an axial Higgs mode, which would have some implications. But for condensed matter theorists, this is not or even condensed matter experimentalists, not so bad, because all it looks like is I have one kind of order parameter, I have another kind of order parameter, and perhaps there's some constructive and destructive interference in these, and that maps out a vectorial potential. Right? It doesn't seem that hard, at least in condensed matter. And that's exactly what we were able to see in this rare earth tritelluride type material, except in this case, our structural order parameter are these charge density wave type systems. And this was a simple experiment. This is an example of complicated theory, simple experiment. The experiment here is room temperature Raman spectroscopy, right? Raman spectroscopy, another very pandemic appropriate experiment, came from a previous pandemic quite some time ago. So now in this past pandemic, used to actually think about pathway interference and the selection rules associated with this axial Higgs mode. And we were able to conclusively establish that this axial Higgs mode, at least in its quasi-particle form, exists in these rare earth tritelluride materials. We were excited about it, and we, of course, this is one of the few times where when we posted this, I got a bunch of high energy colleagues writing and saying, I need to talk to you urgently, now, today. And I didn't respond, and then, of course, went on social media and looked at all the folks who had opinions on the matter. So it turns out that you can have things in condensed matter that don't immediately have an analog in high energy, even if they are inspired by high energy physics. And this is an example of that. But that got us further down the road of actually thinking about what are other ways that you could realize high energy physics in condensed matter in a way that it actually teaches you something about the high energy equivalent of it as well. And one that I have become very, very excited about, some would say even obsessed with, is actually finding Axion physics in condensed matter. So long time ago, Axions, and I'll come back to the slides here in a second, were proposed to actually fix or clean up the charge parity violation problem. And Axion, in particular, the word Axion, Frank Wilczek named this, is actually a name of a cleaning brand, is a dish cleaner that you can find. I haven't bought it, so I don't know if it's still sold, but lots of folks have photos of it, so it was clearly sold at some point, and it would clean up this problem. It's a proposed candidate, some would say a leading candidate for realizing and finding dark matter. But our story is a little bit simpler than that, in that we want to find this axion and also find this axion field, which is essentially thinking about the equation of motion associated with this axion in condensed matter. Now, there are two things here, and I want to very clearly distinguish them because we think about both of them, and I'm only talking about one of them tonight. One, where we're thinking about finding Axion electrodynamics and implications of the Axion field in condensed matter, and the other, which is using materials, using real ideas from condensed matter to actually make detectors think about quantum sensing of axions, okay? The second thing requires its own introduction, talk, and is far too equation dense for we've already gotten quite equation dense, but that is far too equation dense for the situation tonight. But if you're interested, I can tell you about that another time. So what we're talking about tonight is looking at this Axion electrodynamics, starting with the general Lagrangian, and thinking about how once you incorporate the Axion fields, what does that do? What is that theta term? What is this equation of motion? And then how would it manifest in a response associated with our quantum matter? So our first prediction here was actually one that's surprisingly useful, where we realized that this Axion field can actually give you off-diagonal terms in the epsilon tensor. Right? This is something that you would use to describe and think about light propagation, or even think about thermal emission. And something we know is that absorption and emission need to be partners with each other. Essentially, if you can break that symmetry, if you can make that a non-reciprocal process, you can have a one-way transfer of light or energy. And of course, even in doing that, you need to still compensate and make sure you follow the laws of thermodynamics. But realizing that this Axion field in quantum matter could actually give us thermal non-reciprocity was an important one, and we showed that both theoretically and more recently experimentally in magnetic balanced semimetals, where you expect this non-reciprocity. So some of the concepts here I haven't had a chance to describe in great detail, but just want to leave you with this idea that this Axion field has a concrete, optically accessible observable. And that's something that wasn't known previously. In fact, taking this a step further, very recently, one of my graduate students, Olivia Liebman, is thinking about what would this dynamical axion look like. So if I take this equation of motion, and I haven't discussed this in enough detail for you to maybe fully appreciate this, but just to say that if I think about this, I could come up with just the right protocol, optical excitation protocol, in my magical Axion material that actually shows a Kerr rotation modulation. And if I do that, I actually have a smoking gun signature of this Axion in condensed matter. So this prediction is out there, and we're talking with lots of folks about measuring it. This is a Kerr rotation measurement that would, in various scenarios, actually probably involve some complex interferometry. So we'd actually look for a very, very small angle. But compared to some of the experiments being done by our colleagues in particle physics, this would be a simple experiment. I've learned that using the word simple experiment gets people very upset. So now I calibrate what I mean simple relative to building a giant, many mile long experiment, as opposed to something that perhaps is tabletop or at least can fit in a room. So the claim is, and I hope some of you will track this claim over time and hold my feet to the fire, that you could actually, in a tabletop optical experiment, realize such axions in condensed matter. The story could go on, and I'll just say that this intersection between topology, this intersection with high energy physics and non-equilibrium dynamics is actually, it's quite rich. And despite many papers already being out there, I'd say the field is just getting started. There's ideas in actually using topological materials for chiral catalysis. Remember, I brought this idea of chirality and phonons, but thinking about using the topological material itself to select the product. That's an idea that's catching on. There's a whole bunch else in light-matter interactions, including non-reciprocity, that we and others are interested in, and the list goes on. And finally, going back to things that I was talking about early in my talk, with these cavities, these few photon regimes, I think there's a nice intersection to be looked at with cavity controls, non-equilibrium dynamics, and also types of quantum matter. So with that, I'd like to start to conclude and say that I think we have gone now from observing and understanding some of the rules of quantum matter, which of course has been its own endeavor We've gone from understanding the rules of ultrafast dynamics, thinking about these sources from a very preliminary day to where we are today, sources from the attosecond out to hundreds of picoseconds, and we're now going from being observers to choreographers. So this is a really exciting time to be a scientist in this field, and I feel lucky and privileged not only to be presenting this work to you tonight, but also to be working in this field. Some of that is enabled by our funders, and I see some here in the audience, the Gordon Betty Moore Foundation, National Science Foundation, colleagues at DARPA, DOE, and others. And thank you to my group members who've actually really done the work. I talked about the work from Dominic Jurashek, John Curtis, Yanis Petridis in some detail, as well as some of the work on Axion electrodynamics by Olivia Liebman. They've all really contributed to the success. It's their work that I'm discussing here tonight. And thank you all for being here.
Thank you. Do we have any questions? Okay, Darima, please stand up. Tell us your name if you're a member. You know the drill.
My name is Frederica Darima, and I'm a member. Thank you very much for this tour de force presentation. I have a question, but you suggested a suggestion for acronyms. May I suggest PIF and PICM for the photon-induced Faraday effect? So if you want to adapt them, maybe that would be good. I'm actually known for always coming up with geeky acronyms, so these are a little bit whimsical for me. So you talked about many things, and I was wondering some of the applications of these when you talked about the giant magnetic field that you can create. Could this be used, for example, for, we have superconducting magnets for, for accelerators. Could that be an application? Or some other applications? Is it also helping us understand specific physics, fundamental physics effects in matter?
Yeah. So certainly, I think, so thank you again for the acronym suggestions, by the way. That's very helpful. PIF and PICM, I like those. So these actually types of ultrafast magnetic control and these interactions have a lot of applications, including in very high field experiments, the kinds that are involved at accelerators. I'd say that some of these materials or some of these ways of controlling need a little more technological maturity before they can be deployed at an accelerator in the next years, but that's something that we and others are certainly looking at, particularly because we can realize these very high fields quickly and then turn off quickly as well. And the hope is that the dissipation in these systems will be substantially lower, so that's an advantage of doing it. I will certainly think about how we can, at least for materials that you can get in these large single crystal formats, how they can be used relatively quickly. Some of the others tend to be kind of complicated heterostructures, and there are challenges in synthesis there. In terms of fundamental physics we could learn, absolutely. So everything that we're now learning about the nonlinear upconversion in these systems is telling us about magnetic order parameter, things that were not expected, some cases things that were not known. And I think even this claim, for example, I showed the YTO results. YTO itself is a system that was known for some time, but this non-equilibrium control of it is something that's really new, and something that, of course, we showed the boost of TC, but there's other implications of that in even the equilibrium physics of this system. And that was a boring system in the sense that we wanted to start with something where at least the equilibrium properties could be agreed upon. But there are other systems, particularly magnetic topological materials, where there's a lot to be learned both about the magnetic order parameter and the topology using such drive schemes. Yeah.
Red microphone.
Yes, I'm Bruce Kane from the University of Maryland. Are there any systems, either theoretical or experimental, where you can see a DC effect? In other words, a non-equilibrium steady state response that gets to one of these interesting states? Or is it all picosecond, very short-term effects?
So that's an interesting question. Actually, in some of these systems, once the state is excited, it can live for a lot longer than a few picoseconds. Not from us, but there are other reports that this state, particularly the ultrafast magnetic response can be stabilized all the way out of several nanoseconds. Now, I know that's not steady state yet, but I'd say that we're working towards maybe stabilizing it for a few microseconds. And for at least quantum experiments, microseconds is a long time. Yeah. So that's a way of, I guess, calibrating relative to the timescales folks can access. I think it would be interesting to see, at least for the driven topological materials, if there's something we could do where the effect need not rely on staying in this driven state. So once you're there, you're kind of in a locked non-equilibrium state. I'd imagine that would involve some way of preventing all the other thermalization pathways, or at least other interactions with either the lattice or other orders in the system. I'd have to think about how you would design a scheme like that. Yeah.
Bob Terry, I'm a member. Are there any applications here even thought about where you might use this sort of phenomenon to change the state of a sample? Well, for example, change its dielectric properties, change its conductivity.
Yeah.
Or you could use this for photon-actuated switching, which is a great little rabbit people follow in pulse power. I mean, there's opening switches that get driven by light would be exciting and stuff like that. Are there pathways in this research that go this way?
Yes to all of the above. In fact, ideas in non-reciprocity use that already to some extent, where you have one-way propagation of light. So exciting the system, and now essentially you have a one-way switch that you can create. Folks are thinking about implications of that in optical switching. There are types of architectures where that non-reciprocity could be quite useful. The driven and then getting kind of the connectivity to change and modulating that already happens. In fact, that's something that, particularly to study some of these superconductors, folks are using that as a probe of the behavior anyways. So the answer to that is yes. I think a question for how we integrate that with other photonic devices is something that's still being addressed. Most of the materials, barring erbium ferrite that I showed you, is not something that folks use regularly in optics. So that's actually one of the reasons we started looking at erbium ferrite. Yeah. It'd be beautiful if this also happens in lithium niobate. I see Dominique sitting right behind you. So we'd love to expand this to other classes of oxides. And because some of these have the same types of symmetry, I feel confident saying that yes, we should be able to find these responses there. Yeah.
Red microphone back there.
Hi, Katrina Groth, not a member. I'm an engineer, and I'm not even an electrical engineer, I'm a mechanical engineer. So I'm going to come to you from the perspective of, I love the analogy of going from observing to choreography. And I think of that as kind of where we transition from the science into the engineering, the choreography, and making this work. So help me see, when we have these new types of materials, how close are we to getting this into some of the devices that you mentioned, the quantum devices, the 7 types of quantum devices you laid out?
Yeah. So the types of photonic devices, I think that there's a clear pathway for how these could be incorporated. I think some of the ones that I just alluded to, that has a technological trajectory, a technological pathway. I think with some of the materials that we're thinking about for magnetic control, there's a little more work that needs to be done, particularly because those are hard to synthesize. And usually, at least for YTO and some of these others, is sensitivity to how they're aligned relative to how you're exciting them, which seems particularly challenging, at least to me, from a device standpoint. The magnetic topological materials, and actually topological materials in general, even though they're the newest here on the market or on the scene, are, in my opinion, probably ones we'll see out there very, very soon, in part because most of these are synthesized using techniques we know how to scale up, MOCVD. These are not challenging MBE grown materials, ones where you can actually get bulk single crystals from your favorite grower. In fact, some of the growers are famous for bringing a suitcase of these to March meeting to kind of give to their measurement buddies. So I think those systems are actually quite likely to be integrated into devices. Since you mentioned you're a mechanical engineer, I'm excited to hear your thoughts on the thermal non-reciprocity. That's actually one of the areas where we've been essentially claiming that you could get to high temperature quantum devices even because of this this essential non-reciprocity that you can engineer using this Axion field. And I say we claim because we haven't shown that yet, so I'd love to hear your thoughts on how technologically feasible that is. Yeah.
Red microphone.
I'm Bob Hershey. I'm a member. Could you tell us a bit more about superconductivity?
Okay, the question that so when we think about superconductivity, at least a very low-level theorist view, which is what I'll present here, is we need to have some microscopic understanding of what the pairing glue could be, whether it's electron-phonon, whether it's magnon mediated, and that essentially means some understanding of how the condensate comes to be. Of course, predicting the transition temperature is something that we can't do, or at least most people would say it's something that has several layers of assumptions that take it from science to art. At least it's one that's above my pay grade. But the idea is that essentially if I can say something about the microscopic interactions very precisely, perhaps I can write out some set of diagrams associated with interaction. In the right limit, I could tell you why the superconductor is behaving the way it is. More likely what I can do is tell you about the collective excitations that are associated with the superconductor. And this is something that has a precedent from the helium-3 literature, where people talk about is clapping, flapping, all other kinds of collective modes that are associated with that condensate. We can do similar things, not just with well-known superconductors, but also with superconductors that are less known. Now, something that's quite exciting, and you didn't ask this question, but I'm going to take this opportunity to answer it, is systems that also break time reversal symmetry, how to kind of characterize that. And there are reasons to do that with types of unconventional superconductors that people have been talking about more recently. And detecting that is actually pretty hard. So what we have been working on, we and others in the field, are what are signatures perhaps in the optical or other kinds of collective dynamics, collective responses that could be a smoking gun signature of broken time reversal symmetry or of unconventional superconductivity in these systems. But that's something that's work that's underway in our and other groups. Yeah.
Hi, John Burke, not a member, a physicist. So my question is, I see these non-equilibrium states, and I immediately think, can you put them in a superposition of being in two different non-equilibrium states at the same time? And if you can, what are the implications? And if you can't, why?
Okay, excellent question. So the context in which we thought about that was actually this Higgs mode decaying into pair of Goldstone modes. That was the closest we came to then thinking about what is the relation between these two modes that we're excited. They are a result of a non-equilibrium excitation, and could we actually talk about that itself as being entangled pair generation. It's one of the few times where we could claim we have parametric down conversion, and there's certainly some correlation between these states, but we weren't able to establish what that looks like relative to these being entangled and what would be a good measure of entanglement in such systems. Not in this context, but other contexts we're thinking about good entanglement measures for non-equilibrium behavior. Haven't come up with one that anyone can agree on yet. So, yeah, a long way of saying, I wish I had an answer for you right now, but I kind of don't. So.
Other questions? So I had one question. I think one of your slides showed that you had measured a magnetic field of 107 Tesla.
Effective magnetic field.
Effective magnetic field.
And that was one of the reasons why I kept emphasizing that it's an effective field, not one that's at risk of breaking everyone's experimental apparatus. Yeah.
So you're not going to be able to scale it up and help us confine a fusion plasma?
Probably not. Yeah.
Okay, any other questions? If there, we have a question here, Darima.
When you talked about this asymmetry at the end, towards the end of your talk, in terms of the phonons and reversing directions, can this be potentially looked at of having any effect in what we call the dark matter, that there is something different that happens in that we, in what now, or the way we now interpret dark matter?
Yeah, so axions are a leading candidate for dark matter. There's a lot of debate around the mass range and all of that good stuff. We're talking about axion. So like I said, there are two related concepts here. There's the axion quasi-particle as realized in condensed matter, but also using some of these materials and ideas in quantum sensing to find the real axion. And the second is not something I've had a chance to talk about today, but there are some things that we can learn about the axion quasi-particle as found in quantum matter to then hopefully map back to the high energy theory. And there are a couple colleagues that I'm working with on that. I think that it's easy to draw the analogy. It's harder to frame a mathematically precise question around how do you go back to the high energy theory. And that's something that we're working on. Yeah. One of them is Catherine Zurich. She's somebody who comes from the particle physics, high energy background. I'm sorry? No. Catherine is at Caltech. There's another colleague at UCLA, Rahul Roy, who works on topics that are related in this area. So that's something that we've been working on. This is unpublished work, so hopefully we won't get scooped by all our Zoom audience or YouTube audience.
I hardly think so.
Good.
Next question.
My name is Scott Matthews. I'm a member. So I'm trying to understand the difference between the quasi-particle axion in condensed matter and the sort of quote-unquote real axion that might be dark matter. What do your results with the quasi-particle axion say about the existence or non-existence of the other axion, whether it is part of dark matter or not?
So I think it's encouraging that the axion and axion field effects have been found in condensed matter, right? So at least the quasi-particle, as we think about it from a condensed matter standpoint, exists. I don't want to make a claim that that has a direct implication for the real axion to exist or exist in a particular mass range. That's something that we're just discussing, that narrowing that down is really, really hard. And we don't have a mathematically precise way of doing that yet. But the Lagrangian we were writing down, the expression we were writing down, the field theory that's written is the same as what you would expect to see for the real axion term. It's how we think about that theta, and then what that looks like microscopically in a condensed matter setting is something that we're now evaluating. So those are the results that were shown, and then with that Kerr modulation claim, I think that's assuming a few things about that theta term, but then calculating it for real parameters that we expect to find in a material. Yeah. And by the way, I didn't show this, but there are materials that folks have claimed have axion insulator physics, particularly manganese bismuth telluride and some of these layered magnetic topological materials. The reason that we are looking at it from an optics standpoint, because I understand photons a little better than I understand transport measurements, but also because the transport measurements, drawing a direct line between that theoretical prediction and then what is measured is a little bit harder. So yeah. The hope is that this will actually tell us something about the real axion, not just have this one-way street. Yeah.
A blue microphone.
Okay, Maria Zemankova, member. If you could put the slide with the materials in the middle. Yeah, that one.
Oh.
I am curious. No, not the one. The one with the question mark at the bottom. Not that one. New topology, the one, the crystals.
Yes.
The crystals. I'm curious about the question mark. And if you know what the question mark is, what new topological materials you would be able to create, and what characteristics you would actually like to go after.
Right. Okay. So what's the question mark? If I know what the question mark is, Let's see. So what I was trying to capture here is that we've studied and started to see very interesting electric fields, magnetic field, temperature, electrochemistry, all kinds of responses, but maybe there are types of responses we haven't thought about so far. I'd say a lot of emphasis so far has been on linear. So an easy answer to that question mark that's not on this slide would be extreme nonlinearities. So I'm not just talking about second, third harmonic generation, but really high harmonic generation in these topological materials, perhaps finding ways of doing things that we can't with existing nonlinear materials. That would be something that would have real applications as well. There's, I think, a pretty robust way of doing inverse design in materials discovery. I think that exists, and there's so many topological materials that have either been predicted or materials that have been found to be topological in the past few years that I suspect that even within each of these categories that's on here, we'll find things that were quite unexpected. And certainly we're finding new topologies every day. So, even since this slide was created, there are other kinds of higher order topologies that have been found, not only other higher order fragile topologies, but even some robust topologies that have been found. So, yeah.
I want to thank Bree for giving this talk. And a small token of gratitude for her coming here and giving the talk. We have 3 gifts for her. We have the rosette of the Philosophical Society of Washington, now known as PSW Science, which has on its side the coil of the symbol for induction, which was studied in America, especially by our founder, Joseph Henry. And we have a copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. That is not as boring as you might think. It has a discussion of why the society was founded, why it was called the Philosophical Society, and it has an interesting exposition on how scientific discourse should be conducted that is actually really informative and probably should be required reading for all graduate students, postdocs, junior professors and senior professors and other people who do science. And then finally, we have a framed copy of the announcement of Pree's talk. So please join me again in thanking her for coming here and giving the talk. And before you go, we have a very few closing remarks. Our next talk, at the 2,484th meeting, will be on November 3rd. The speaker will be Ted Schultz, curator of Hymenoptera at the Smithsonian National Museum of Natural History right here in Washington, D.C. As some of you may know, Hymenoptera comprise the ants, wasps, bees, and sawflies. There are over 150,000 living species of Hymenoptera that have been described, and 2,000 species that have been described that are extinct. And a variety of these species are agriculturalists that will be speaking about the convergent evolution of agriculture and species other than humans that are pretty good farmers. The 2,485th meeting will be on November 17th. The speaker will be Bob Truog of Harvard. He'll be speaking on defining death, in part because of differences in legal definitions. A person legally dead in California may be legally alive in New Jersey. Recently, one authority modified one of the definitions of medical death that is widely but not universally accepted. The subject involves a complex mix of competing viewpoints of politicians, lawyers, scientists, doctors, cultures, religions, philosophers, and ethicists, and is a microcosm of how these differences can be reconciled or not, and resolved or not, in our democratic, diverse, and multi-jurisdictional society. Please check the PSW website often for up-to-date information on meetings and lectures. Please thank our crew for manning the cameras and organizing things tonight. And finally, all this doesn't happen on its own. It takes a fair amount of work on the part of a great many people to do all the things we do, to have a nice reception, dinner, and lecture. So we need help. And if anybody in the audience is willing to lend a hand, please see me. We are certainly looking for new blood, so to speak. And with that, I will entertain a motion to adjourn the 2483rd meeting of the Society. I'm sure Bob will want to make the motion, and AJ's got a second. All members in favor? Well, anybody opposed to adjourning? No? Meeting is adjourned.